Hello everyone, this is Sajid Ahmed, your physics teacher. Today we'll be doing an interesting chapter, the pressure and density. So see here, first of all I would like to give you an introduction about the physics. Physics in the sense it is a subject which is 100% practical. Okay, not even a single percentage of that which is derived from the other side. I mean, when you consider the other subject and physics, the physics is a subject which is 100% practical, which you can feel everything in your life. Okay, so in that, out of all the chapters in physics, for me I would consider this pressure, density, such topics are very much familiar for you from your childhood. What do you feel? It doesn't mean that with the equations you have to derive. It's very much familiar. We'll just go through that. Now, the pressure, in the sense, what do you feel? Just say, if a point pin knocks you, or else a hammer knocks you, you might be feeling two different kind of feelings. Just say, I'll take you through this. The pressure. We can see this duster. In this duster, if I push with this pin, right, the duster, you can very clearly see how I pressed here. Just say there might be an area covered. See, if this is the duster, I'm using this pin. Because of the pin, the pressure exerted in a certain area. At the meantime, I can even use another pin, okay, and apply the same pressure on it here, but the pressure applied in a very smaller area. It's so tiny. Therefore we can get it. See here, the area which the force is applied, if the particular area is smaller, the pressure is very high. But if the area is higher the area, the pressure is very less. I'll show it down. Just say, if I'm applying a force of 5 Newton to this duster, and also say to this duster, 5 Newton for the area of 3 meters. Just say, for our convenience, we can take five meters, and here the same force I'm going to apply, the 5 Newton, but the area is only 1 meter. Let's say 1 meter squared. Ultimately, the pressure which is applied here is 1 Newton per meter squared, but here it is 5 Newtons per meter squared. In the sense, if I'm applying the force through a bigger area, the pressure is evenly spread, and therefore we can get a very low pressure. But if it's pointed, it applies to a very certain area, and therefore the pressure is very high. It comes to 5 Newton per meter squared. So simply you can get the whole of it. Just say the pressure applied is inversely proportional to the area. So we can mark it like pressure applied is inversely proportional to the area. Yeah. Now, the pressure, there are two kinds of pressures. If you have a solid object, in that solid object, what pressure is applied, that is according to the area and the force which is applied. But just say inside a liquid, inside an ocean, if you take inside an ocean or a container, if there is something, a small object, we can even find it how much pressure does this particular point feels, or how much pressure is being exerted on that. It is, just say there is a water column above the particular object. I'm just using another color. Above the water column, which tries to push this particular object. See here, the equation we use to find the pressure exerted at a certain point in a water column or in a liquid column can be found by the equation the pressure is equal H rho G. H is the certain height above the particular object or above the particular point, and the rho, the letter rho, is the density of the liquid around this, and the G is the gravitational pull. So under a liquid, if there is an object or if there is a certain point, okay, we do have another different equation to find it. It's not like the pressure is equal force upon area. That is actually for the solids, okay, and on top surface of a solid, how much pressure is being exerted, we can find with that equation. We do have another equation to find it under a liquid column, or else, you know, just at a certain point above water column or by the above liquid column, how much pressure is being exerted. We do have a different equation. P, the pressure is equal H rho G. So it depends on the height, on the density of the liquid, and the gravitational pulse. Since we all are here in the earth, the gravitational pull is the same. So unless if we go to another planet, you know, it won't change. So see here, my dear students, at this point, just say if the height is 20 centimeters, if the height is 20 centimeter, and if you take water here, water's density is 1000 kilogram per meter cube, and the gravity, as we all know, that's 9.8, so we can take it as 10. So here, how do you find this particular point? The pressure which is being experienced by this point is P, the pressure, H rho G. H is 20 centimeter. We do not keep the length or the height in centimeter, since the SI unit, the standard international unit for that, is meters. So we have to divide it by 100 and multiply by the rho. Rho is actually 1000 for water, and multiply by 10. So we'll be getting the answer. Cut 1 0 1 0 1 0 again 1 0. So we'll be getting an answer 2000 Pascal. We do have three equations, three units for the pressure. One is Pascal, ATM, and Pascal is there, ATM is there, and the third equation is what we derive from here. The force is Newton, areas, SI unit is meter squared, so it would be Newton meter minus 2. So I hope this little interface would be clear for you. So I'm going to erase it, I'll just move on to the next slide. Now we'll be looking at density. If someone comes and asks you what is density, in one word we'll have to say it's just the thickness. Thickness is the density. Say I'm going to give you 2-3 different kind of liquids. Okay, one is water, and the other one is you say the mercury, and the third one say grease. It's a kind of a semi-solid. I'm going to give water, mercury and grease, right? Water, mercury, grease. So if I'm giving, you're supposed to find it by the thickness. See here, the water, how the water can flow through, or how the thickness, we can very simply say water's density is very lesser in compared to these three. Hydrocarbon is the highest one, and the grease in between. So see here, these all things can be found logically, practically. We can see and say, we can measure these all by the thickness, how thick or how easily it can flow. But through the equation, the density is equal mass divided by the volume. It means how much mass can be contained in a unit volume. So volume's unit is meter cube. The mass will be in kilograms. So how much kilogram can be contained in a unit volume? So that's density. So here we can find the density of a certain object or a certain substance given. Let's move on to some questions in these related to the pressure and density. I'm going to give you several points. Here, one point, and another point, another. So we can even label it A, B, C, D, E, F, G, H. You see, these all are different containers. It's a beaker. This one is like a test tube, and this is a small beaker, and this is a different structure. Though the structure changes, what do you think about the pressure in these points? It's a kind of a question. What do you think about the pressure exerted at this point? The answer would be the pressure is everywhere, here, everywhere. The pressure is same, because the pressure doesn't depend on the area of the container. It depends, the liquid pressure depends only in the height, density, and the G. Since the G and the rho are equal, we have to consider the H. So at all these places, A, B, C, D, E, F, G, H, all the places are at the same height. These all experiences the same pressure. So the pressure is pressure at A equal to B equal to C equal to D, E, F, G, H. And one more for your understanding, we can do another question. We'll get another clear picture about the pressure with another illustrated diagram. See, it's a container. In this container, I'm going to make 3 holes. Here, a hole called A, B, C. see here, it is full of water. This is full of water everywhere, full of water. I'm going to make 3 holes in these 3 places, and I'm going to check which place, at which hole does the water comes faster. See here, I want you all to just guess whether it will be here, here or here. So from these we can understand, we can get to know at which point the pressure exerted is more. Now generally the pressure exerted at this point would be more. The water, the liquid would be thrown away further apart, far apart. But here it's not like that. It's the distance from here, from the bottom to here, bottom to the place where the water is coming is lesser than the previous one, and the C part is rather lesser. Do you know the reason why? The reason why it is, see here, at this point C, the pressure, above this point C, there is only a water column of this length. This height is only there, H1. But if you take this B part, the B part, here there is a big water column from here up to here, here up to all the way here. And furthermore, if you take the A, the point A, it is having the more water column, H3. So since the height is proportional, see here, is directly proportional to the pressure, we can say, here we take the height as the depth. Height is actually the depth. We don't count it from here to here, we count it from the top to bottom. So how much water column is there, that amount of water column give a pressure, exert a pressure on these points. Therefore here at A, the point A experiences the most pressure, so we can put the pressure in descending order. Pressure at A is higher, then the pressure at B is little lesser, pressure at C is rather lesser. So that's the basic idea about pressure and density. So we'll be having another lesson, and I hope to meet you in the next lesson. Let's wind up the lessons. Thank you.